We're going to graph a second type of function. Our first one that we did was polynomials. This one is rationals. We'll spend today and then finish it up like at the start of class tomorrow, just last minute questions. And then on Thursday we have a third type of function that we graph, but they all kind of go through that same sort of feel. I am looking for important pieces. And remember, when we're graphing polynomials, because polynomials are continuous functions, all I need to know is the x-intercept, the y-intercept, and where it changes directions. Rational functions are not always continuous functions over the domain of all reals, meaning there are spots in a rational function where there's a hole or where there's an asymptote, and that is because we have a denominator. It is still very helpful to find certain things, and in rational functions we look for four main things, and that's our x-intercept, our y-intercept. We look for asymptotes, and then we also look for holes. So those are our four main things that we're going to look for. Like with polynomial functions, it is nice to have an idea of what they look like. Now, you guys learned about the parent function in Algebra 2 if you took Algebra 2 here. And that parent function is just the inverse function, 1 over x. Does that look familiar? And as you added stuff to the x, it would slide this left or right. As you added stuff after that fraction, it would move things up or down. But that function looks like this. Has those curves. And along those curves, we have asymptotes. We have horizontal asymptotes and we have vertical asymptotes. And I think you spent a whole big chapter in Algebra 2 working on that. So our graphs are going to base themselves off of this inverse function. Now, rational functions are not limited to only this look, because as you square x and again add and subtract things to it and put variables up on the top as well, it adjusts them. So we have basically so probably 3 different variations of graphs. Now, when I say variations, I mean it could have this feel, other than maybe this bottom one would move up to the top and the top one would move to the bottom, or maybe they're both up on top, or maybe they're both going down on the bottom. So it would have that feel where I just have an asymptote and an asymptote. Our other type of graph that we're going to see has 2 asymptotes, and it will have this feel. Has 2 vertical asymptotes, I should say. It is going to have a region on the left that it sort of follows, kind of similar to the parent function. It will have a region on the right that it sort of, again, follows similar to the parent function. And then it'll have a little curly Q thing that goes through the middle. And again, this second type of graph that we see could have, both of these in the bottom region here. This could be flipped, so it's sort of the opposite twist, but it has that feel. 2 little loopy-doos on the outside and a little curly Q on the inside, okay? The last type that we're going to have besides the parent function is another one where we have multiple asymptotes. But on this one, I'm going to have my 2 little loop-de-loos on each side, those 2 little curly things on each side, and then I have sort of a parabola-looking thing in the middle. So just know that these are our 3 end results that we're going to have on our graphs today. Again, rational functions are not limited to this, but these are the ones that we're going to see. And we know what it is by finding the zeros and the y-intercept, all of those pieces, because again, just like our polynomial functions, I can't cross an axis unless I'm invited to. So if something does not have an invitation to cut through the axis, it will not. And so that's going to tell us if we go up or down when we're creating our graph. All right? So first things first, we are going to start by factoring if necessary, meaning if it's already factored, obviously I don't have to, or if it can't be factored, I can't factor. So when I look at problem number 1, can I factor this? No. Okay? So then I'm going to find any holes. Holes happen when you have, let's say I'm just going to give you an example, like I have x plus 3, x minus 2. I went and factored my thing, and then I have x plus 3 over x plus 4. A hole happens when I can cancel something out. And we saw this when we were doing limits. That if I took a limit on this, I would end up with 0 over 0, and that told me I could factor or do something algebraic. And so when I'm looking for the hole, my hole is at x equals negative 3. It happens when whatever I could cancel out equals 0. Okay? So then I look back down to number 1. Are there any identical quantities in the numerator or denominator that I can cancel out? No. So there are no holes on problem number 1. So now I get to the big part of it. This is what these next 4, this is prep work. These are going to get me my graph, okay? These next 4. So I need to find my zeros. My zeros are my x-intercepts, and I do that by setting the numerator equal to 0. So I'm going to slide this down. We don't need to look at that up here. You have it listed on your paper. So I am going to find my zeros. I'm going to set the numerator equal to 0. And I write that as a point, bless you, negative 2/3, comma, 0. Because all I'm really doing is setting the function equal to 0, that's what it is. And then it's 0 equals 3x plus 2 over x minus 4. I get the x minus 4 out by multiplying it out of the denominator, leaving me with 0 equals 3x plus 2. So my shortcut is just set the numerator equal to 0. The denominator is going to multiply out. Then I find my y-intercept, that's next in line, my y-intercept, and I do that always the same. The y-intercept is found by replacing x with 0. So essentially I'm finding f of 0. And so that's 3 times 0 plus 2 over 0 minus 4, or negative 1/2 when I do my math. And that gets written as the point 0, negative 1/2. My next piece is, if I look at all of these functions, I have this imaginary line that these can't cross. In these second 2 that I drew here, there are 2 of those imaginary lines that my graph can't cross. Those are called vertical asymptotes. And vertical asymptotes happen when the graph is undefined, and I find that by, I abbreviate vertical asymptote with VA, I find that by setting my denominator equal to 0. And I write it as a line. It is the line x equals 4. And then my last one is my horizontal asymptote. And my horizontal asymptote is found by taking the limit of the function as x approaches infinity. So this is what we did back in chapter 8. I am going to, horizontal asymptote, I am going to take the limit as x approaches infinity of 3x plus 2 over x minus 4. Do you guys remember how to do that? When I approach infinity, I look to see if it's top heavy, bottom heavy, neutral. What do I have here? Ooh, I've got disagreement. Where is the highest power?
No.
There isn't one. Yeah, power, not number, yep. So then I isolate my lead terms and reduce it down. Remember, these things are like nothing compared to infinity, the 2 and the 4. And so I reduce that down and I get a value. Does that ring a little bit of a bell? Hopefully. This is my horizontal asymptote, and I write it as a line, a horizontal line. Remember, vertical lines are x equals, horizontal lines are y equals. I need to talk about a horizontal asymptote just briefly. They can be crossed. Horizontal asymptotes only give us end behavior. So what it does is it tells us where the graph goes on its extremities, far left and far right. In between, you can graph a or cross a horizontal asymptote as many times as you want. As long as the graph gives it an opportunity to cut through by opening a hole on the x-intercept or on the y-intercept, you can cross it. Vertical asymptotes, not the case. So vertical asymptotes are the one that we're just going to hover right up next to. So I'm going to put this all together, and it seems always at first like this, there's no way this is going to be enough to sketch this graph. But if you know how functions work and what each of these things mean, it is more than enough. My 0 is at negative 2/3 0, so I just put a little dot on the negative side. And again, I don't get too crazy. If you feel like I need to put a number next to that, go for it. I'm not going to. I just know that it's on the negative side of the y-axis, on the x-axis. And then I do my y-intercept, and that's at 0, negative 1/2, so I just put it pretty close to the x-axis, but on the negative side of the x-axis for the y's, on the y. Then I do my vertical asymptote. That's over here at positive 4. And then I do my horizontal asymptote, and that crosses at y equals 3. And now I put it together. Remember, my end result is only going to be one of 3 pictures, or a variation of those pictures. And everything I have here is, I can cross it if it lets me. So, for example, these 2 points are going to connect. That's going to cross the x-axis at that one on the left. It's going to cross the y-axis at this one below. And then it's going to approach the asymptote. And this other one's going to approach the asymptote as well. It's going to approach this guy. Now, there is an offbeat chance that at some point this function comes back up and comes down, but it's a minute little piece in it, so we're not going to worry about that. I just know where my end behavior is, and it's going to approach that asymptote, that horizontal asymptote, on the far left. On the far right, because I'm not going to have a piece of this graph above here, because then it's not a function, it fails the vertical line test. So I took up this side. So I have a left piece, I have a right piece. On the far right, it cannot be in the lower portion because there is no spot for it to cross the x-axis. So the only place this graph can go is up in that upper area. And I'm done with that graph. If there were another x-intercept here, then this little loop-de-doo thing would have to come down and be in that position. But there's not. It can't cross the axis without permission. And if I don't have an opening for it, then it's got to be in the other region. So this is kind of like our very first example of the graph. Any questions? Okay, let's do our next one. Go through the process. Can I factor this? Yeah, I can. I can take a 2 out of this guy. that out. It's not going to make that much of a difference if I did it or not, but I can, okay? So then, next, I'm going to check to see if there are any holes. Are there any identical quantities? Yeah, the x minus 4. So I'm going to cross those off, and I'm going to make a little note to myself. There is a hole at x equals 4. Now I have to be careful. Yes? X plus 1. Thank you. Thank you, thank you. 2x plus 1. Appreciate it. All right. There's a hole at x equals 4. It's on the function. It's actually on the point x comma f of 4. Okay? It's on the function, and we'll approximate where that is when it is. It's not on the x-axis. All right? So there's my hole. Up next, my zeros. So I'm going to take and set the numerator equal to 0. So 2 times x plus 1 times x, oops, nope, the x minus 4 is gone, equals 0. When does 2 equal 0? Never. So that's a non-issue. When does x plus 1 equal 0? Yep, and so I have a 0 at negative 1, 0. Then I'm going to find my y-intercept. And that is at f of 0. And so that's 2 times 0 plus 1 over 0 plus 3, or 2/3. The hole is out, so I don't need to worry about it. The hole is gone. I don't need to bring it back in when I'm finding my y-intercept. I don't need to bring it back in when I'm finding anything else. It's gone. It's a hole in the graph. We removed it. Now I'm going to find my vertical asymptote. That's when the denominator equals 0. And I'm going to find my horizontal asymptote. And that is the limit as x approaches infinity of 2 times x plus 1 over x plus 3. I do need to remember that this is 2x plus 2. I know I factored it earlier, and x plus 3, because that 2 is attached to the x, making my limit 2. So y equals 2. And then I put it all together. I have a 0 at negative 1. I have a y-intercept at 2/3. I have a vertical asymptote at negative 3. I have a horizontal asymptote at 2. I know what's got to happen on the far right, because I had those points in there. Remember, there's not going to be anything above this on the far right. It can't be, otherwise it fails the vertical line test and it's not a function. So now I have to go to the far left. Is it going to be in the upper region or the lower region? Upper. And I know that because there is no spot for it to cross in the lower. The lower is what contains the x-axis. I do not want to forget my hole. So I'm going to go back into this graph. I'm going to approximate where 4 is. And I'm just going to add a little hole on my graph. And I just do it just kind of tiny. I just make it look like there's a spot where it was out. If you feel like you want to erase it and make it a real hole, great, but this usually does the job. So our first two graphs were like the very first parent function. The next are going to be the ones that have that extra vertical asymptote in them. So I'm going to start by factoring. X minus 3, x minus 1, x minus 4, x plus 2. I factored my function. Are there any holes? Is there anything that has identical quantities that I can cancel out? Nope. So no holes. I'll just make a note to myself, no holes. Zeros. Tell me how I do it. Yeah? What's that? Set the numerator equal to 0. So x minus 3 times x minus 1 equals 0. That means x is 3 and x is 1. Are we okay with that? Is my math good? So I have two of them, one at 3, 0, and one at 1, 0. Y-intercept. How do I do that one? F of 0. So that means f of 0 is 0 minus 3 times 0 minus 1 over 0 minus 4 times 0 plus 2. Looks like I get 3 over negative 8. So that's at negative 3/8. Nope, it's at 0, negative 3/8. 0, negative 3/8. Vertical asymptote. How do I do it? Bottom equals 0. So that means x minus 4 times x plus 2 equals 0. I have one at 4 and I have one at negative 2. So I have two vertical asymptotes. You will find as you do these, as you get comfortable, as you move along with them, that you will be able to find these things with very little work. And then I'm going to find my horizontal asymptote, and my horizontal asymptote is the limit as x approaches infinity of the function. I am going to use the original form of the function because it is easier for me to pick out my highest term, highest power. And sometimes I won't be able to do that. I'm going to have to figure out what I think the highest power is. And so it's just sort of not actually multiplying it through, but envisioning what's going to happen. Here my highest power is squared. It's neutral. That reduces down to 1. So I have a horizontal asymptote at y equals 1. Now that I have all of my pieces, I put it together on my graph. One 0 and 3, 0. Negative 3/8. Positive 4 and negative 2. And y equals 1. Put in my zeros on the x-axis, my y-intercept on the y-axis. I put in my vertical asymptote as imaginary lines approximated about where they are. My horizontal asymptote as a horizontal imaginary line. And now I need to put this together. I'm going to go on the far left. Is it in the upper region or the lower region? Has to be in the upper because it doesn't have any place to cross the x-axis, and I know what that side looks like. Then I'll go to the far right. Is it in the lower region or the upper region? Upper again. It has no place to cross the x-axis, so it's going to be on that upper region there. In the middle, I have two choices. Either it's going to S through and cross the axis at one spot, or it's going to loop around and cross the x-axis at two spots. What do I have here? Looks like loop around. So I make my little loop around. And that's kind of what I look for. Is there two spots where I cross, or does it twist through in one place? Yes.
So you said it needs to cross the horizontal.
Yep, it can. And this might go up here and cross. I don't know. I'm not picking points, so I don't know exactly how high that value is there, and I don't really care. I just want to get a general look at the graph. So when we do the ones that twist through, those are the ones that for sure cross. And there are other times when, if my point was up here, then this would have to go, like if my y-axis was here, you get what I'm saying? It would have to curve through that way. And then it would cross that axis there, the horizontal axis. This one just happened not to. All right. I didn't have any holes, so I didn't have to put them on. Let's give this one a try. We're going to talk through this one again even a little bit quicker. So I'm going to go through that same process that I did before. I'm going to start by factoring. So this is the opposite of, and in fact, what I'm going to do is I'm going to assign that negative up to the top. Just I don't want to lose it, so I don't want to keep it in front. So this is x plus 9, x minus 1 over, on the bottom I'm going to factor that, x plus 3, x minus 3. Any holes? No, nothing that can be canceled out. So then we'll go through our process again. Zeros. When the opposite of x plus 9 times x minus 1 equals 0, this is like negative 1, and negative 1 will never equal 0, so it's going to be a non-issue in this problem. This one's at negative 9. This one's at positive 1, and I write those as points. What makes x plus 9 0? Negative 9. What makes x minus 1 0? Positive 1. Y-intercept, f of 0. That is the opposite of 0 plus 9 times 0 minus 1 over 0 plus 3 times 0 minus 3. On the top, that's going to leave me with a 9. On the bottom, that's going to leave me with negative 9, and negative 1 is what I get for my answer. That is the point 0, negative 1. Vertical asymptote. X plus 3 times x minus 3 equals 0. So x is negative 3 and x is positive 3. Vertical asymptotes, two of them. And my horizontal asymptote, the limit, as x approaches infinity. I'm going to take it from the unfactored form. It is the opposite of x squared over x squared is really all I care about. I can write, it's going to act like this. I can write all the rest of it, but I don't need it. That is negative 1. So it's at y equals negative 1. Let's see if you can put it together. Let's go in order. Negative 9, 0, that's kind of way over here. 1, 0, 0, negative 1, negative 3, positive 3, and negative 1. Here's an example where I have a point that is on the horizontal axis, and that is okay. What is not okay is a point on the vertical axis. So I have to take that out if that happens. On the far left, I know where it has to go. It has to cut through the axis. On the far right, I know where it can't go, because it can't cross the axis. In the middle, does this do a loop around like our last one? Does it cut through that axis twice, or does it snake through? Because I've only got one point that it goes through, it has no other way to be welcomed back through again. It's going to be a snake. Yep. Could it bounce? In order to have a bounce, we need to have 2 zeros at the same place. So yes, it could if this factored down to x plus 9 times x minus 1 times x minus 1. And I don't have that. I need zeros of multiplicity in order to do that. Okay? All right, our last one. Already factored, I don't need to do that. Are there any holes?
Yeah.
Yeah. Where?
X minus 3, x minus 3.
Yep. So there's a hole at x equals 3. Remember, it's on the function, not on the x-axis. But there's a hole at x equals 3. That's when x minus 3 equals 0, so it's the opposite of whatever that is. Then I go with my zeros. I have them at negative 2, 0, and 1, 0. Look how lazy I'm getting. Are you okay with me being that lazy? Do you get what I'm doing? Is that okay? I'm just taking this and I'm setting it equal to 0 without having to write out all that work. And it's okay for you to do that, because you should be pretty quick at doing those things. All right? Then I'm going to find my y-intercept. And my y-intercept is going to take these guys that are left, and it's going to be 2 times negative 1, 0 plus 2, 0 minus 1, over 1 times negative 2, or negative 1. Again, I just put 0 in there, put 0 in there, put 0 in there, put 0 in there. That's the point 0, negative 1. Yes? Positive 1? Positive 1. Wait a minute. Positive 1. Thank you. Okay. Then I do my vertical asymptotes. And again, now I'm looking at just the denominator. I have one at negative 1, and I have one at positive 2. All I did again is just take the denominator, set it equal to 0. When does x plus 1 equal 0? When x is negative 1. When does x minus 2 equal 0? When x is 2. This is going to be the hardest one, my horizontal asymptote, and that is because this is all factored. So, if I were to multiply the numerator together, what would be the highest power? How many x's do I have? 3 of them. I have, 2 of them in my, because I took out that 1, so I have 2 of them. So my highest power, my limit as x approaches infinity is going to act as though it has a highest power of squared on the top. Again, because the x minus 3 is gone. How is it going to act on the bottom? Same way, like x squared on the bottom. Do I care about all the other garbage that comes with it? No, because end behavior only looks at our highest powers. And so I end up with a limit of 1, and so I'm going to graph that as y equals 1. And then I go to my graph, and I put everything together. My zeros, negative 2, positive 1. my y-intercept at 1, my asymptotes at -1 and +2. Make sure that you're putting it in the right location, because I'm not numbering my graph, so I just want to make sure that I put it in the right location. If that x-intercept is at 1 and the asymptote is at 2, that I know that that's to the right. And then another time where my horizontal asymptote goes. All right, I am going to freeze this, and I want you to see if you can sketch your graph. And then we'll compare them. Anybody need more time? Okay. How'd you do? How many of you remember the whole? Did you? Good, good. That's a common thing that people forget. They forget the whole on the graph. So, again, we're limited in what we're looking at. You have 3 basic different graphs that you're going to look at. The things that you have to do is kind of figure out, is it in the upper, is it in the lower, is it a squiggle in the middle, is it a curve in the middle, or kind of parabola looking thing? So let's